In this video we are going to calculate this integral using complex calculus, and in particular it is the integral of 1 over x to the power 7 plus 1 in the denominator from 0 to infinity. We will see that this integral is much easier to compute in complex calculus rather than using simple calculus, because when doing calculus, if you have such a denominator, if you want to find the antiderivative of 1 over x to the 7 plus 1, you have to make a great effort. It can be done, of course, it can be done, but the effort is greater than the effort that you have to make in complex calculus. Anyway, let's consider the denominator. The denominator is x to the power 7 plus 1, so it is a polynomial of 7 degrees, and we have to find the roots of this denominator. In particular, if we want to find the roots, we have to set this denominator equal to 0. Therefore, x to the 7 equal to minus 1, and so we have to find the 7 roots here. In particular, minus 1 can be written as e to the I pi, and we also have to add, to be more general, plus 2k pi, where k is an integer that goes from 0 to 6, 0, 1, 2, 3, 4, 5, 6, if we want to find the 7 roots. So if we take root 7 of minus 1, here on the right we have to divide this by 7. And when we set k equal to 0, we have the first root, which I will call x0, equal to e to the I pi over 7. Whereas when we set k equal to 1, we have x1 equal to e to the I 3 over 7 pi. Then we have x2 when k is equal to 2, e to the I 5 over 7 pi. We have x3 equal to e to the I pi, because we have e to the I 7 pi over 7, and of course we can simplify that, and this is equal to minus 1. And so on and so forth. We have other roots, but the roots that we are going to consider are these 4. And I will show you why we need these 4. Because let's consider the sketch of where I represent these roots. x0 will be somewhere here, so we have an angle here which is pi over 7, this angle here. Then we have another root somewhere here where the angle here is 3 over 7 pi. We have another one somewhere here where the angle is 5 over 7 pi, and this angle is greater than pi over 2 because pi over 2 could be written as 3.5 over 7 if you want pi. And therefore, pi over 2 is in between x1 and x2. Okay, so this is x2, this is x1, and this is x0 or x0. And then x3 is on the x-axis because it is minus 1. And I'm not going to draw the other roots which are in the bottom part of this plane because I don't need them. What I need to do now is to choose a contour. The contour that I will choose goes like this. We start from the origin, then we move on the x-axis like this, and we are going to enclose the first 3 roots like this, but at some point this semicircumference is interrupted, so I interrupt this semicircumference and we will consider the radius of this semicircumference r to go to infinity, as is usually done when we want to evaluate real integrals. This is a semicircumference. As I said, I have interrupted the semicircumference somewhere here, and then with a straight line I'm going back to the origin. I am doing this because it will simplify the calculation of the integral if I leave out this minus 1. Otherwise, if I go back onto the x-axis, I have to be careful and avoid this discontinuity, something like this, okay? But I'm not going to do this. It's easier if I calculate the integral like this by using this straight line and go back to the origin. And then I travel this path anti-clockwise like this. Let me call the entire contour gamma, where gamma is the semi-circumference plus this line plus this straight line on the horizontal axis. We know that according to the residue theorem, if I calculate the integral over gamma, which is a closed contour, of the function f of z dz, where f of z, in this case, I will define it like this, 1 over z to the 7 plus 1. This is equal to 2 pi I times the residue of the function f evaluated at x0, which is e to the I pi over 7, plus the residue of the function f evaluated at x1, which is e to the I 3 over 7 pi, plus the residue of the function f evaluated at e to the I 5 over 7 pi, and that's it, because the contour contains only 3 roots, and these roots have multiplicity equal to 1. So we have to calculate these residues if we want to calculate the integral. The residue of the function f evaluated at e to the I pi over 7 is just, as you know, for poles of multiplicity equal to 1, we have to multiply the function by z minus the root, which is e to the I pi over 7, and then we divide by z to the 7 plus 1, which is the function f itself, right? So we multiply the function f by z minus e to the I pi over 7. And we have to calculate the limit of this as z goes to e to the I pi over 7. We can use the L'Hopital, right? So we can take the derivative of the numerator and the denominator. So we have 1 over 7 times z to the power 6. And then we have to evaluate this at z equal to e to the I pi over 7. We can also rewrite this in a more convenient form, like this. We can rewrite it as z over 7 times z to the power 7. I've simply multiplied the numerator and the denominator by z, and we still have to evaluate this at z equal to e to the I pi over 7. Why did I do this? Well, because now in the denominator I have z to the power 7, but z to the power 7 is e to the I pi over 7 raised to the power 7, which is e to the I pi, and e to the I pi is minus 1. So in the numerator, we get e to the I pi over 7, whereas in the denominator, we get minus 7. Now something similar for the other two residues. We have the residue of the function f to be evaluated at e to the I 3 over 7 pi. And by doing the same trick as we did above, we get almost the same result, except that in the numerator here we get e to the I 3 over 7 pi divided by minus 7, and something similar for the residue of the function f evaluated at e to the I 5 over 7 pi is equal to e to the I 5 over 7 pi divided by minus 7. So our integral over gamma of dz over z to the power 7 plus 1 can be split into 3 parts. The first part is on the x-axis, if you recall. So we have to go on the x-axis here. We integrate from 0 to capital R, where R goes to infinity, but now let me just write R. And in this case, the function will be a function of x, because we are integrating over the real line. So we have dx over x to the power 7 plus 1. And remember that R goes to infinity. So I can simply replace R by infinity. Then we have plus the integral over the semi-circumference here. And in this case, I have dz over z to the power 7 plus 1. And I will rewrite it as integral over the semi-circumference. And when we let r go to infinity, you can prove, the same way we did in other exercises in complex calculus, that this second integral will give a zero contribution. Essentially because the magnitude of the denominator will grow larger and larger, and it will annihilate this integral. It will make it go to zero. And finally, we also have to consider the integral over this line here, and we can parameterize the line like this. We know that z in that case is equal to some parameter that I will call t. The parameter t will take into account the magnitude of the vector measured from the origin. So when we are at this point, for example, t will be equal to the radius of the circumference, r, and when it reaches this point, the origin, it will be 0. But we also have to multiply by the phase of this complex number, which takes into account this angle that we have to measure from the x-axis. So we have e to the I, and I can choose an angle between this angle here, that's the phase of the root x2, and that angle is just 5 over 7 pi, and this other angle here for the root x3, which is just pi. We have to choose an angle in between these two. For example, I can choose the angle 6 over 7 pi because it is greater than 5 over 7 pi and it is smaller than pi. It has to be smaller than pi, otherwise in our contour we would also include this discontinuity, which we do not want to include. But we need to enclose the point x2, so this angle must be greater than 5 over 7 pi. That's the angle that I will choose. So we have z equal to t e to the I. Now let me cancel this one here because I don't need it and it will just take up too much space. E to the I 6 over 7 pi. This is the parameterization that I will consider in the last integral. So I have dz, which is e to the I 6 over 7 pi dt, and then I divide by 1 plus z to the 7, but when I raise t times e to the I 6 over 7 pi to the power 7, I will get t to the 7 times e to the I 6 pi over 7 multiplied by 7 here in the argument of the exponential. So I will cancel this one with this one. But e to the I 6 pi is just 1. So we get t to the power 7 here in the denominator. And we have to integrate from t equal to r to t equal to 0. And also let r go to infinity. So we can rewrite these integrals like this. Integral from 0 to infinity of dx over x to the 7 plus 1. I can change the sign in the second integral and integrate from 0 to infinity here, because here r goes to infinity, remember that. And then I have dx, let me change the name of the variable t to x, dx over 1 plus x to the 7, and outside the integral I can multiply by e to the I 6 over 7 pi, and this is equal to 1 minus e to the I 6 over 7 pi times the integral from 0 to infinity of dx over 1 plus x to the power 7. Now remember that we started from this integral here, and this integral here is also equal to 2 pi I times the sum of the residues enclosed by the contour. So we have 2 pi I times the three residues that we have calculated. So we have the residue of the function f evaluated at the point e to the I pi over 7, that's just the first root that we called x0, and we have minus e to the I pi over 7 divided by 7, then we have minus e to the I 3 pi over 7 divided by 7, minus e to the I 5 over 7 pi divided by 7. And now we can divide both sides by this number, so we get integral from 0 to infinity of dx over 1 plus x to the 7 equal to 2 pi I. I can put the minus sign before 2 pi I, and I get e to the I pi over 7 plus e to the I 3 over 7 pi plus e to the I 5 over 7 pi divided by 7 times 1 minus e to the I 6 over 7 pi. Now you can do your algebra on this number on the right, but this is already our result. This is the result of our computation. We started from a real integral on the left, so you have to make sure that this right hand side is also real when you do your algebra. And if you do the algebra, you can prove, if you have a calculator that can deal with complex numbers, you can simply just insert this number into a calculator and it will do the job for you. You can show that this is approximately 1.034376055, something like that. So that's a real number.